or to the cloud. All right, so we are now recording. I'll pop over here. And where we left off last time, I think we were watching some videos, right? What we'll do this time is, now that we kind of got introduced a little bit with the videos, hopefully you can remember and visualize what was going on, right? He had the oscilloscope and he was kind of simulating waves going down in the one direction, and then there were waves bouncing back the other direction. And then he added the math function to add them together, and you saw some kind of weird patterns. And he put on the infinite persistence, which basically just kind of filled it in, right? Kind of filled in all with red. And the thing we're interested in, this is important. It's easy to get confused about what we're talking about here. The thing we're interested in is the envelope. What does the envelope mean? Well, let me just try to draw something. I'll probably draw this poorly, but bear with me. So let's say you had a sine wave. Okay, so let's see you had a sine wave and it was growing in amplitude, and then maybe it was shrinking in amplitude. The envelope of that would basically be like the peaks of it, right? So what we're interested in is this interference pattern between the incident and reflected waves, because what it does is, in some places, the two waves traveling in two different directions add constructively and create an overall voltage that's bigger than the original one was. Or they add destructively and they kind of cancel each other out. And so you're left with a lower voltage than what you would expect it to be if there was only an incident wave. So in order to see that, we just want to know, like, of course, it's all varying with time, right? Everything we do is AC. So everything's oscillating like crazy. Like normally we're dealing with things in the gigahertz, billions of cycles per second of a sine wave, up and down, up and down, up and down, right? But we're interested in the envelope of it, like the peak of it, the amplitude of it. In some places on the transmission line, where things add together, let's say destructively, you'll still have a wave that's oscillating at our frequency, but because of the destructive interference, the amplitude there will be smaller. If there was no reflected wave and you just had a regular old sine wave going down and you plotted the envelope, so you had just a regular old sine wave, that's constantly going up and down, it's constantly oscillating with time, right? If you did the envelope, it would just be a straight line. Nothing interesting's happening. It's just a regular old thing. But because we have that reflected wave, they interfere. Some places, like here, maybe there's constructive interference and it gets a little bigger. And maybe over here, there's destructive interference and gets a little smaller. That's why we're interested in the envelope, the kind of extreme of the wave, because it tells us where the destructive interference is happening and where the constructive interference is happening and how much of each is there. We got to calculate it then, right? You kind of saw it, and we're going to see it again because I'm going to pick up that video kind of where we left off. But we want to calculate it. So the way we're going to calculate it is we're going to calculate the magnitude. Okay, we're going to calculate the magnitude. The magnitude of what? The magnitude of the voltage on the line. Because remember, our voltage on the line can be expressed like that, where this first part describes the incident wave, and the second part describes the reflected wave. So we've got both baked into this. Now, I recommended last time that you memorize it if you can, but if not, have it on your formula sheet. Gamma, that's our reflection coefficient. The capital gamma. Our lowercase gamma is something very different. The lowercase gamma is that weird curly one that is our propagation constant, right? The capital gamma is our reflection coefficient. This part here, the V0 minus over V0 plus, reminds you of what the definition of the reflection coefficient is It's the amplitude, if you like, the amplitude of the reflected wave divided by the amplitude of the incident wave. Tells you how much gets reflected. And then the ZL minus Z naught over ZL plus E naught, that's how you're actually going to calculate it. Normally you have ZL and Z naught, so you're able to actually plug numbers into that one and get the answer. If we just looked at this part, well, then we could easily just rearrange to solve for V0 minus, right? You would just bring the V0 plus over. You multiply gamma by V0 plus, you get this. And then we could say, well, you know, if V0 minus equals this, then, you know, we could just plug that in there, right? And what would we get? We get V tilde at Z equals V0 plus E to the minus J beta Z plus gamma V0 plus E to the minus J beta Z. We've got a V0 plus and a V0 plus. So we could factor out the V0 plus. So that's what we have here. Exactly what we did at the top. We substituted in gamma V0 plus for V0 minus. We then just have to factor out the V0 plus. Yeah. Thank you. There is not. So negative there, not a negative there. Okay, thank you. Okay, so this is the form that we are going to use usually from now on for the voltage at any point on the transmission line. It's a completely equivalent to that one. It's the same thing, but we're just going to write it this way. All right. We can do the same thing with the current. Let's not worry about the current too much. Okay, it's just the same. You can see it's just, you know, divided by Z naught basically, and maybe there's a sign difference. But if we know the one, we know the other. We're mostly focused on the voltage. So what do we want to do? We want to get the magnitude, because that's the thing that's going to give us the envelope. Okay, we want that envelope. So here's a bunch of ugly stuff that we're going to go through. But the first thing we need to think about is, how do we calculate the envelope? How do we calculate the magnitude? And so what we want is the magnitude of V at Z. That's what we want. Now we know ways to calculate magnitude, like if you have a complex number in rectangular form, you can do like the real part squared plus the imaginary part squared, and then you take the square root, and that's a magnitude. That's good. Another way to calculate magnitude is to do the thing, in this case, V at Z, and then you multiply it by V at Z complex conjugate. And then you take the square root of it. So that's another way that's equivalent to calculate a magnitude. All right. So let's say we did that. Well, we have a V at Z, the one that we want to use here, right? The one that we found over on the right-hand side. So what else can we add in there? Well, what is gamma? So what do we know about gamma? We know it's the reflection coefficient, right? We know what we wrote up top there, V0 minus over V0 plus. We know it equals ZL minus Z naught over ZL plus C naught. We also know it's a complex number. Remember that. I think I mentioned last time, people always lose marks on midterms and finals because I say, find the reflection coefficient, and then people just give a magnitude. They forget the phase. So it's got a magnitude and it has some phase. Theta R is the phase angle of the reflection coefficient. Okay, so we pretty much got everything we need here. So if we look back up to our slightly modified expression for voltage on the transmission line, up the top right, we want to get that one first, right? That's just regular old V at Z. That is that one. but we could just plug in our definition of what gamma is. So V0 plus e to the minus j beta z. This is just regular old gamma broken up into its magnitude and its phase. Okay. And then we have the e to the j beta z. Okay. That covers this one. Now we need to multiply it. So we're going to multiply it by this thing's complex conjugate. Okay, you have to think maybe back to your math classes a bit. We don't know what's inside V0 plus, but we'll just put the star there to say, whatever it is, well, we need to worry about it. We need to take its complex conjugate. If you're in rectangular form, you know, real plus j imaginary, you just can flip the sign, right? And if you're in polar form like this, you can just flip that sign to do the complex conjugate. So we got to do the complex conjugate of that because it could have some phase angle. Note here, all we've done is we flip the sign there, right? Minus goes to plus. Plus goes to minus. Plus goes to minus. Okay. All right. Now we got to multiply it. You might be like, well, that's a pretty ugly thing to multiply, right? But it's not that bad. So first of all, this thing's outside of all of this and this thing's outside of all of that, right? So if you multiplied that one by that one, V0 plus times V0 plus conjugated, and then take the square root of it, that's the definition of magnitude, right? That's just like what we had right there, but for V0 plus instead of for V at Z. So that's why we can pull out the V0 plus and the absolute value or magnitude signs. So that's where that goes. Just from the definition of how you can calculate a magnitude, you take the thing, you multiply it by the complex conjugate of the thing, you take the square root, that is the magnitude. All right, then we got to do, so if we take those out, we can forget about the V0 plus. So we're left with what's in these brackets times what's in there. So let's take it one at a time, right? We got to multiply this one by that one, and that one by that one, and that one by that one, and that one by that one, right? Just normal multiplication. What would you get when you do that one times that one? Yeah, 1, right? Because you can add the exponent. So e to the minus j beta z times e to the j beta z, the values add together and then they go to 0. You have e to the 0, e to the 0 is 1. Boom. That's that one. Okay, question. Yes. Yeah. So basically what we're doing here is similar to this, but I'll just write it. I'll go V0 plus magnitude equals V0 plus times V0 plus complex conjugate, square root. That is like a fundamental equation or definition of how you calculate magnitude, just like we had, you know, real part squared plus imaginary part squared, take the square root. And if you want to convince yourself of that, just pick any complex number, put it in rectangular form, 3 plus j6 or something, right? Calculate the magnitude of it. If you did it the usual way, you'd go 3 squared plus 6 squared, square rooted, you get a magnitude. Then try it like that. Be 3 plus j6 times 3 minus j6, because we have to complex conjugate it, and then then you have to take the square root of it. If you went through all that, you would see that they're the same. So there's just 2 ways to calculate magnitude that are equivalent. So that's where that one goes. The one is from the e to the minus j beta z times e to the j beta z. What next? Well, what if we did that one, the magnitude of gamma times e to the blah, 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 times the magnitude of gamma e to the minus j blah, blah, blah. What would these two, when you multiplied those two, what would that come to? Yep. So these would be e to the 0, but we got the gammas up front, right? So when you took care of all the complex exponentials, they'd all go to e to the 0, that would be 1, but you'd still have magnitude of gamma times magnitude of gamma. Magnitude of gamma squared. The last one, well, you can kind of see it, right? Like you're multiplying that one by that one and that one by that one. So that one times that one, see they both have an e to the j beta z in them? So e to the j2 beta z. And the same thing with the other one, but the negative. So really you just need to be careful. You're multiplying each one and you're not gonna need to do this. We're heading to kind of the final form we're gonna deal with, which is close to this. You don't need to rederive this, but it's important to know where does this come from? So what can we do here? That's just for fun. Call that x. In other words, x equals 2 beta z plus phi or theta r, which means that's also x. Which means what we have here is like e to the jx plus e to the minus jx. All right, e to the jx, we can use our Euler's formula. That would be cos x plus j sine x. E to the minus jx, that's the same thing, but we just have to flip the sign. So if we did e to the jx plus e to the minus jx, we're adding these two. So the j signs go away. But we're left with two of the coses. So we have 1 plus gamma squared, magnitude gamma squared, plus 2, because when we add these two together, we've got 2 cos x's, where x is 2 beta z plus theta r. And we still have our magnitude of gamma in there. And it's still all to the power of 1/2 because it's all a square root because of our basic formula here. So we kind of did it. Any questions about that? There's many steps there. You kind of have to go through it carefully. But like I said, you're not going to have to redo the derivation. Just remember the big picture where this comes from. Okay, one last thing we're going to do. Remember we talked last time about z's and d's, and we said to make our lives easier, we are going to define z equals 0 to be at the load, which means we go negatives if we got to go back to the source, because z has to increase as you're going from the source to the load. And then we said, well, working with negatives, well, that's sometimes a little annoying. It'd be nice if we worked with positives. So we defined something that we just basically said d equals minus z, right? So if we wanted to plug that into there, then what would we have? We'd have this would become cos minus 2 beta d plus theta r, right? Cos is an even function. Starts at 1, right? But it's the same. My drawing's terrible, but the curve is the same on the left side of 0 as it is on the right side of 0, which just means that the cos of x equals the cos of minus x. In other words, you can multiply the stuff in here by -1 and it equals the same thing. So if we multiplied the stuff in there by -1, well, that would become positive 2 beta d, but then minus theta r. positive 2 beta d minus theta r. That's our final form for the expression that describes the envelope of this interference pattern caused by two waves traveling in two different directions with potentially different amplitudes. This blue trace up at the top right was what in the video was trying to be shown by when you put on the infinite persistence and it filled in with red, and the envelope, the magnitude, had some kind of sinusoidal shape. That blue trace describes the amplitudes at different points on the transmission line. So look at your x-axis there. We're dealing with distance from the load. So you've got your transmission line, you've got a source, it's connected up to here. You've connected a load on this end. When you first turn it on, like in the initial instances, right? It takes some finite amount of time for the wave to travel from the source end to the load end. So you got some wave, it's traveling down the line. At that time, and that time only, there's no reflected wave because it hasn't reached the end yet. It's got to get there before it can reflect, right? So for that very short period of time, you know, you could calculate what it is. If you can figure out what the speed is, the UP, that's meters per second. The line has some length in meters. So you could figure out the time it takes the wave to go from the one end to the other. After it hits the end, now you've got a reflected wave, okay? Now you've got the incident wave and the reflected wave both coexisting on the same transmission line. They're adding together, causing constructive and destructive interference. At some places on the line, they add together constructively. So that would be like there, okay? At other places, they tend to kind of cancel each other. Sometimes they'll completely cancel each other. We'll see that shortly. But this is a more generic case where they kind of cancel each other and they kind of add together. So the x-axis here is d, meaning distance on the transmission line from the load, okay? All right, so we got an expression for the voltage and the current. The current's shown below, but like I said, we're mostly concerned about the voltage, so let's not, I'd say just note that the peaks of the current correspond to the minimas of the voltage. So this one at the top right actually describes a specific case here. A gamma of that, 0.3 e to the j 30 degrees. And the magnitude of V0 plus equals 1 volt. So the magnitude of gamma is 0.3. So that tells you right away, it gives you a sense of how much is getting reflected back, right? Like 30% of the amplitude of the incident wave is going to be reflected back. And it causes a phase shift that has a phase shift of 30 degrees. The incident wave has an amplitude, think sine wave, think, you know, your labs down the hall. When you go to your function generator, you choose sine wave, you choose your frequency, you choose your amplitude. You set it to 1 volt, that's this case. And what we get is at the top right. So how do we get that curve? So what I'm saying is that blue curve is described by that. So let's think about how that and that equation and this specific example all kind of line up. How do they all coexist? All right, if you've got your calculator, we can punch in some numbers. So first number you can punch in, or first number you don't even have to punch it in, you can just think about it. Just this part. Just the cos, the part that I've underlined in red. Without knowing anything about 2 beta d and theta r, What's the biggest that thing can be? Like if you went crazy in your calculator and you said cos of this number, cos of that number, cos of whatever, it can't be bigger than 1. Cos is restricted between 1 and -1. So the biggest it can be is 1. So let's play with that case. Let's just say, we don't know where that peak happens yet, but let's just say we're at the point of the maximum. And we're saying that for now, we'll consider that cos term to be equal to 1. And that allows us to calculate the rest. So if you had your calculator and you do 1 plus the magnitude of gamma squared, 0.3 is the magnitude. So it would be 1 plus 0.3 squared plus 2 times 0.3. And we said for now, we're considering the cos term to be equal to 1, which is at its peak. What do you get? What was that? 1.9, and then take the square root of it. Can someone confirm that? That seems like it might be a little bit off. 1 point. Great. So just double check it. I think it should be 1.3. So what did we just calculate? Well, if you look at this equation, you go, we assume for now that the V0 plus is set, it's fixed. And our gamma, think about what gamma equals, ZL minus Z naught over ZL plus Z naught. We're assuming that we're not changing the ZL like in the middle of our, as the circuit's running or something like that. And Z naught is the transmission line. We're assuming we're not changing it midway through operating the circuit. So ZL's set, Z naught is set. So gamma is just fixed at this value. In other words, it's not changing up there. V0 is not changing. We're assuming it's set. So the only thing in this that can change is the part I've underlined. Okay. The biggest it can be is 1. We just did that case. We got 1.3. Therefore, we would say that the maximum that it can be is 1.3. So like right there, you can see over here, it's right in between 1.2 and 1.4. That's where they add together constructively. The only thing that changes in this equation is the cos term. So let's do it the other way. What's the smallest cos can be, or the lowest? It's -1. So you do the same thing. You go 1 plus 0.3 squared plus 2 times 0.3 times -1. Then you'd have to take the square root because we're doing the magnitude, calculating it the way that we did. And if you did that, you'd get, and you can check this, but you'd get 0.7. So just from doing those two extreme cases, we're able to find what the maximum is and what the minimum is. And those are two of the most important things. That tells us the level to which we are getting constructive interference and destructive interference. Everything in between, well, it just is going to depend on the value of that cos 2 beta d minus theta r. Theta r is fixed, right? It's just part of the gamma. So it's just 30 degrees. Be careful when you punch those sorts of things in though, because does anyone remember some expressions for beta? What values, what is beta? Its name. Phase constant, that's right. It's a tricky one because it's easy to mix up phase constant and the propagation constant, right? But it's the phase constant. Units of beta, what are the units of beta? Close. Radians per meter. Radians per meter, okay? Can anyone remember an expression, an equation for beta? Yeah, I like that one. Beta equals 2 pi over lambda. We have some other ones as well. The other ones work too. This is just a nice one to work with here. 2 pi, that's good. We can punch that into our calculator. What about lambda? Can anyone remember an expression for lambda, our wavelength? What was that? UP over F, yeah. So lambda is UP over F. All right. F, we normally know F. We're not changing F. You are almost always going to be given F for a problem, okay? Or in the real world, if you're actually working on a product, you know F, right? Like if you're designing some Wi-Fi thing or whatever, you know exactly what frequencies that has to operate at. So we know F. UP, what's one way we can calculate UP for a lossless line? What's that? I got these things and it's harder for me to hear, that's why. Okay, anybody have a comment on that? It might be, it could be, you're not necessarily wrong. Is it always the speed of light though? No, we can't necessarily assume it's the speed of light. And lossless doesn't tell you the velocity. It doesn't tell you if it's the speed of light. However, if it's lossless, there's a really, really easy equation you can use for UP. For lossless only, UP is C divided by the square root of epsilon R. So now we can kind of outer conductor has an epsilon R of 9. Okay, it's a bit high. This would be more like 2 or 2.2, but I like 9 because you'll see why in a second, right? So what would UP be? Yep, because C is 3 times 10 to the 8. We would divide that by the square root of 9. So it'd be 1 times 10 to the 8 or just 10 to the 8. Okay. And then we'd come over to lambda and we'd have 10 to the 8 for UP. And we'd have 1 gigahertz, that's 10 to the 9 for F. So we have our lambda. Lambda is 0.1 meters, right? 0.1 meters, that's 10 centimeters. So you can kind of think about what 10 centimeters is, right? So then we come over to beta. Beta is 2 pi divided by lambda. That'd be 2 pi divided by 0.1 or 20 pi radians per meter. Now we got beta. So we know V0 plus typically, as long as we know ZL and Z naught, we know gamma. We just figured out what beta is. We know theta R, the only one left is D. D is the distance from the load. So it's just depends, how far back do you want to calculate it? I want to calculate it here. I want to figure out what it is here or here. If you were in MATLAB, you would just say D equals 0 colon 0.01 colon 0.1 or something, right? And it would calculate it at all the different points. It would go through this expression. So D's the one that's changing. As D changes, it goes through the cos from +1 to -1 and everything in between, which is changing how much gets added in this term here, because it's always 2 times magnitude of gamma times something that's changing. And that's what produces that plot up at the top right. So this gives us our V max, which you can see is here, and our V min. And we're about to define something called the standing wave ratio, which is everywhere, even more common than gamma, but really telling you kind of the same information. The standing wave ratio, as we'll see in a minute, is just V max divided by V min. So if you have these areas where you get like this really big cancellation, and then areas where it really, really combines together a lot, then you'll get a Vmax that's way, way bigger than the Vmin. And the standing wave ratio is Vmax divided by Vmin, so you get a bigger standing wave ratio. If you only had like a very small amount of interference, like constructive and destructive, then your Vmax and your Vmin are going to be pretty close to each other. There's not much interference happening. And so your standing wave ratio would be close to 1. That's normally desirable, all right? Okay, in this case, our standing wave ratio would be 1.3 divided by 0.7, which is 1.86. To give you a sense of what that means or a practical application, if you look up pretty much any antenna, you graduate, you go and you work for Lockheed and you're designing a radar system for their latest fighter, and you need an antenna for it. So what would you do? Well, they would have their own antenna designers, likely. I think there's a former student of mine who's working there now doing similar things to that. You could design your antenna, or you could just look up companies that sell antennas. You go, someone's already designed this antenna that works at my frequency, my power level, it fits the right size, all that kind of stuff. You just buy it, unless it was really expensive or something like that, right? Or maybe they don't have it and then you have to design it yourself. In any event, let's say you were going to buy it from another company. You'd look up their data sheet to make sure it meets your specifications, your requirements, and pretty much guaranteed they are going to give this S. They won't call it S though. They'll call it by one of its other names. It's an important one, and so it's got a bunch of names. It's called the standing wave ratio, right? It's called SWR. It's so common, people just say SWR. It's really, though, a voltage standing wave ratio, right? Because we got it by dividing the maximum voltage divided by the minimum voltage. So people also will call it the voltage standing wave ratio, or the VSWR. And sometimes when you're talking to people, people also just call it the VSWR. Okay. So pretty much any RF microwave component that you look up a data sheet for, they're either going to give you the standing wave ratio or the gamma. Okay. So I'm just going to jump ahead here for a second because we were already talking about this. We're going to come back to this here. So we already did a calculation with it. Here's the definition. Vmax divided by Vmin. And if you looked at where the Vmax occurs, it's when we had that case of where the cos equals 1. And you could simplify that down to just 1 plus gamma. And for the Vmin, that was where the cos term equaled -1. And if you plugged in -1 for that, you can simplify it down to 1 minus gamma. It's the magnitude of gamma though, okay? So if you are given gamma, or you can calculate gamma, it's easy to calculate the standing wave ratio. So in our example back there, the magnitude of gamma was 0.3. 1 plus 0.3 divided by 1 minus 0.3. Bang, you've got the standing wave ratio. If you're given the standing wave ratio, though, can you calculate gamma? Only half of it, right? So the standing wave ratio, like look at this equation. 1 plus a magnitude divided by 1 minus a magnitude. Magnitude is always just a real number, right? It's a length. That means S is always a real number, meaning it's a scalar, it's not complex, it doesn't have an imaginary part, it doesn't have a phase angle, none of that. It's just a plain old number, okay? So you could certainly rearrange this equation and solve it for the magnitude of gamma, and you'd be able to get the magnitude of gamma. But as I said, gamma has a magnitude and a phase, okay? Okay, so that is VSWR. So we'll come back to that. So let's go back to where we were, and we are here. So this is pretty much what we've already been talking about. We get this interference pattern. We have a maximum value that occurs when that cos term equals 1. And then you could say, well, when does this cos term equal 1? And you go, well, where does cos equal 1? And you'd say, well, it starts off at 1, right? Cos starts off at 1, sine starts off at 0. So cos starts at 1, so cos of 0 equals 1, okay? And then it's a cosine, so it repeats itself every 2 pi, right? So it peaks at 0, 2 pi, 4 pi, 6 pi, 8 pi, right? So the way we can write that compactly is just to say it peaks, the cos equals a 1 when 2 beta d minus theta r, that's the argument of the cosine, equals 2n pi, where n equals 0, comma 1, comma 2, comma dot, 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 right? So with the 0 in there, well, that just says 2 beta d minus theta r equals 0. Cos of 0 is 1. We're at a peak of cosine. That's going to be a peak of our voltage magnitude. And the minimum occurs when the cos equals -1. When does cos equal -1? Starts off at 1, right? And it ends off at 1, right in the middle, which is pi, or 180 degrees, cos equals -1. So that's why we have this here. Imagine the easiest one is if n equals 0 again. Then it would just be 2 beta d minus theta r equals pi, okay? Okay, so if we have no reflected wave, life is good. We don't have a standing wave. There's no interference. We just have that nice case of just one wave coming down, and the magnitude isn't changing with position on the transmission line. And this last point here is just to say, just remember that the voltage is actually oscillating. Everything, sometimes we draw these curves like this, and you might get the false impression that we're dealing with like DC stuff or like really slowly changing voltages, but we're just dealing with the envelope, the amplitude of it. Really, this thing is going up and down like crazy. It's oscillating like mad, right? Billions of times a second, all right? All right, so we watched these 2 videos last time, and we were in the middle of this one, right? So let's finish it. We'll see if I can get the sound going again, and I'll try to get to about the right place. So I'll have to take my AirPods out.
For the morning, where books meet Black Mecca. Should you move to Canada? Long lost score, finding your voice in a place far away.
This powerful $99 drone is now available in the US. This is an extremely high-tech $5,000 drone.
All right.
It was
Okay.
In today's video, we're going to talk about kind of visualizing RF standing waves that can occur on a transmission line when it's not properly terminated in the lines, on the line here. Well, again, it helps to put the persistence on here. So let's make an infinite persistence, and we can actually see that the sum of those things creates this beat pattern, actually, that has got nulls, or what we call nodes, at every half wavelength. And then we've got peaks or antinodes at the other half wavelengths. So the amount of power that we'd measure, if we measured power at different points on the line, would be different depending on where we measured it because of that standing wave. Now, it might be a little bit harder to visualize as what happens if the reflected waveform is not at the same magnitude as the incident waveform. So I'll simulate that by turning the amplitude down on my reflected waveform. I'm going to go down to about half of what the incident waveform is. And what happens when we sum these together? If we turn that math trace on, we can see we still get a sine wave, but it's kind of bouncing and moving a little bit, and so it's kind of hard to see what would happen with the standing wave. But again, if we turn infinite persistence on, it becomes kind of easier to see. So we see we still get nodes, if you will, every half wavelength, and peaks every half wavelength. And essentially it's, you know, we go from that kind of half wave rectified thing to something that's a little bit softer, but we still have a standing wave. In fact, you know, the voltage standing wave ratio that you hear about is really a measure of the forward waveform amplitude and the reflected waveform amplitude. What we're seeing here is essentially the sum of those two things and how you actually wind up getting a standing wave out of that. So in order to visualize the standing wave on an actual transmission line, I'm using this kind of open line here, a strip line. It's about 4 inches long. So we can actually measure the voltage at different points on that line. Now, in order to see a standing wave, we've got to consider the wavelength of the RF signal that I've got coming from the RF source here. In a strip line like this, the speed of propagation is about 6 inches or a little over 15 centimeters per nanosecond. So we have to consider the period of our RF signal, and to ensure that we at least get a half or more than one period or so contained within that strip line. So I'm using actually a 2.5 gigahertz, actually a 2.4 gigahertz RF signal coming from over here. And on this transmission line will give me a overall wavelength of about 2.5 inches, which is, about that big or so on this transmission line here. So we should be able to see, a couple of nodes and antinodes in the standing wave. But to take a look at the RF voltage that we have on the line, what I'm going to use is this little RF detector probe. I did a video on this as well, just a couple of germanium diodes and a couple of capacitors to detect the RF power. So we'll be able to probe at different spots along the line and actually visualize that standing wave. I'll start off by putting a 50 ohm termination on the end of the line. And let's probe the voltage on the line. I've got the scope going at a very...
Predictions. What do you think is going to happen? So you just put, he has a source connected up, right, to the one side. And it's a 50 ohm transmission line. Z naught equals 50 ohms. And on the other side, his is that board, right? But just to see it, he put a 50 ohm load. Any predictions? What would gamma be? Let's forget about the overall prediction. How would we figure out what gamma is?
ZL minus ZL over.
ZL minus Z naught. Yep.
Over the addition.
Right. ZL gamma equals ZL minus Z naught over ZL plus Z naught. So then you'd say, well, what is ZL? It's a 50 ohm load. That's what he said. He was putting a 50 ohm load on. So it's 50. So that's ZL minus Z naught. That's the characteristic impedance of the transmission line, which is 50. So in the numerator, we have 50 minus 50 divided by 50 plus 50. So we have a gamma reflection coefficient really close to 0. It's like 0, right? All right. So then we need to take the next step and go, if we have a reflection coefficient equal to 0, what does that mean in terms of what we're going to see here? Straight line. Yes. Because remember what we're kind of plotting is the interference of the two waves, the incident wave and the reflected wave. The reflected wave, its value, its amplitude, if you will, is gamma times the incident wave amplitude. So we're going to have 0 times whatever the incident wave amplitude is, meaning the reflected wave amplitude is going to be 0 or very close to 0, which means there's nothing to interfere with the incident wave. If we've removed the interference between the two waves, we just got a regular old sine wave. It's just moving down the line. So its amplitude is not going to change because the only reason that amplitude changes is because of the constructive and destructive interference. So if he puts this on, it should be just kind of like when he puts on the infinite persistence, it'll just fill all in. And if we just looked at the envelope or the magnitude of that, it would just be a straight line. Okay.
Slow sweep speed, so we can actually see the trend as we take a look at this. So if I put the probe on here, You can kind of see, you know, the RF amplitude here, it's about 1 division. I'm not going to care about the actual voltage here. It's just about 1 division or so on the screen. And if I work my way down to different spots on the line, you can kind of see that it's about the same voltage no matter where I measure it. In fact, if I very carefully slide this down the line, I get both contacts on there and slide it down the line. All right. You can see there's a little bit of variation here. There's a little bit of a standing wave, and that's because this termination is probably not perfect at 2.5 gigahertz. Me probing it introduces a discontinuity, which is going to add some reflections, and this line is probably not perfectly 50 ohms. So I think it's certainly acceptable that you're going to see a little bit of a standing wave. Okay, not a tremendous amount, but a little bit as we slide this down the line. And we can actually see that as we trace it out. Of course, things will get a whole lot more dramatic if we remove the termination here and leave it as an open circuit. We're going to get kind of that perfect termination or perfect reflection off of that open circuit. And we should see a pretty strong standing wave here. So if I stick the probe onto the line at this end here, see at that point I see very little RF energy. If I slide down the line here, you see the RF power coming up. So right about here on the line, we're sitting, pretty close to, a max power, a whole lot higher than I saw before. Let's slide down the line a little bit further. You can see the voltage coming down right about here. It reaches a minimum. There's one of our nodes. We go another half a wavelength further down the line. My RF power comes back up again. Okay, so you can actually see that standing wave. In fact, if I try to move this linearly at a constant speed, we should be able to trace out that standing wave pattern. Let's see if I can do that. I'm going to try this one more time to see if I can get a nice clean picture of that standing wave pattern. All right, here we go. There we go. That was a pretty clean picture. I scooted along pretty at a constant speed here, and I can actually see that standing wave pattern that looks just like the envelope of what we saw on the Wikipedia page, as well as in the RF measurements that we did earlier on the scope. And I hope you enjoyed this short little video on visualizing RF.
Okay, so anyone have any questions about what we saw there or what he did or anything along those lines? So remember what happened? Open circuit part when he took the 50 ohm load off. When he took the 50 ohm load off, what happened was the ZL is now, what is ZL when he took that load off? Infinity. An open circuit is infinity for the load, okay? So then you think, all right, well, I need to use that gamma equation, ZL minus Z naught over ZL plus Z naught. ZL's infinity, so infinity minus Z naught, infinity minus 50 over infinity plus 50. Forget about the 50s compared to infinity, right? So infinity over infinity, it's 1. Gamma is 1. If gamma is 1, that means the reflected wave, which is V0 minus, and V0 minus is gamma times the incident wave amplitude. So they have the same amplitude, but they're traveling against each other. So in some places, those two amplitudes perfectly line up and you'll get twice the initial amplitude, but in other places, they'll be perfectly 180 degrees out of phase and you'll get close to 0. So that's why you got this kind of crazy looking wave where it actually adds up and goes above the incident wave at some places, but then goes to 0 at other places. Okay, so matched line, that's what we saw, right? There is no reflected wave, there's nothing to interfere, it's just a straight line. That's often what we want because reflections, unless you want them for one reason or another, usually you want to deliver all your power to the load. You want to deliver everything to the load and have it accepted and do whatever it's going to do with it, right? We didn't see the short-circuited line, we saw the open-circuited line. But you can see that they're pretty similar, they're just shifted. Okay, now this is a wild thing that I'm telling you here. This is crazy, okay? Take the short circuit. Boom, you shorted it out at the end. I go on here, I short the center conductor to the outer conductor. I put like some connector on there. And you'd go, well, that's a short circuit. And if you said, well, what's the impedance looking that way towards the short circuit? And you go, well, it's a short circuit. Short circuit has a 0 impedance, right? Okay. And if you said, well, what's the voltage? If you're measuring voltage between, let's say, the center conductor and the outer conductor, because you always have to measure voltage between 2 points, right? So you've shorted out the end, you measure the voltage between the center conductor and the outer conductor, but you literally just connected them together, right? With a piece of metal. So the voltage is going to be 0. There's not going to be any voltage difference there. But the crazy thing is, if you just come in a little ways, and by little ways, let's say a quarter of a wavelength, and we know how to calculate wavelength, right? We just did it. So you come to this point here, and instead of getting 0 for the voltage, you actually get a peak. And what you actually get, and we'll see it shortly, if not today, then next time, what this means is that the impedance changes. So if you're looking towards the load, if you're at the load and it's a short circuit, it looks like a short circuit. But if you come back from the load a quarter of a wavelength, it's indistinguishable from an open circuit. Even though you put a short circuit on it, you come back a quarter of a wavelength, you look towards that load, even though it's a short circuit, you would not be able to tell the difference. It will behave exactly the same as if you left it open circuited, which is totally non-intuitive, I think. Same thing with open circuited line. So if you open circuited it here, if you went back a quarter of a wavelength, it's going to behave like it's a short circuit. And everywhere in between too. So we're going to look at that a lot next. So the distance between kind of the period that you could say is like, it repeats itself every half of a wavelength. So we have gamma equals 0 if it's matched, -1 for short, +1 for open, like we talked about the last time. Note that for these open and short cases, we go up to double the incident wave voltage. This is one of the reasons why it's so important. Because if you're dealing with that case I talked about before, you're dealing with a radar system. And if it's a radar system, it's probably going to be pumping out a lot of power, because the way it works is it sends out a wave. It could go kilometers or miles, right? It hits something, maybe another aircraft or something. So when it hits it, the electromagnetic wave gets it bounces all over the place, right? But some of it will bounce back to you. So then you need to send it a lot of power so that it loses power as it's traveling out there, hits the target, only some of it bounces back to you, and then it's got to go through all that free space path loss to get back to you. Then you have to receive it, right? And so you want to start off with a lot of power so that it can handle the loss there, the loss from the reflection, and then the way back. So you're dealing with a lot of power, which means you could be dealing with really high voltages. And then if it wasn't matched, well, in the worst case, like an open or short circuit, you're already dealing with a high voltage, and then it can be doubled, right? If you don't have it terminated properly. So I might have mentioned this before, but a place where this actually, you could see this was in my previous job. I was doing research for the Department of National Defense of Canada, doing electronic warfare stuff. And they had like a man-portable system, and it was high power. And so one of the kind of notices on the backpack thing to the Army soldiers that would wear it was, do not turn this thing on unless you have an antenna connected to it, right? Because if you've got an antenna connected to it and the antenna is designed right, the antenna would be designed to have a low gamma, a low reflection coefficient, which means a wave comes down to it, it doesn't get reflected. If it doesn't get reflected, that implies that it gets radiated, okay? Which means you'd have like the matched case, okay? But let's say you didn't have the antenna connected. Now what you really have is an open circuited line. So you'd send this wave down. Gamma would equal 1, ZL minus Z naught over ZL plus Z naught. ZL equals infinity, infinity over infinity equals 1. You get places where it doubles the voltage that was already high to start with. You get damage to the transmission lines. There's electronics connected to this thing at the one end. And so what's in electronics? Transistors. All transistors have maximum voltages that they can handle. And so the reflected wave producing a standing wave could add constructively and cause damage to your electronics or damage to your transmission line, these sorts of things. Okay, so hopefully we have, I've sold you on this business of constructive and destructive waves and adding together and creating maximas, minimas. But we want to be able to know, well, where does the maximum occur and where does the minimum occur? And we're able to calculate this just based on what we've already talked about. Because the only thing that's varying, that's causing it to go up and then down and up and then down, is the coast term. All right. So if we're interested in the maximum comes when that coast term equals 1. And so if we plugged in 1 for that coast term, we'd have 1 plus gamma squared plus 2 magnitude gamma. We could factor that. Okay. We could have it as 1 plus magnitude of gamma times 1 plus magnitude of gamma, which is 1 plus magnitude of gamma squared. And then we have a square root. So we're left with just this simple formula, 1 plus magnitude of gamma. So all that we did that last time in that example where I was like, plug in the numbers, magnitude of gamma was 0.3 and you had to plug it all in and then you took the square root of it. This is a simpler way to do the same thing. So that is the value of Vmax, but we want to know, where does that occur? And we already talked about it. We said, well, it's going to be when the argument of the cosine, the thing in the parentheses, cos whatever, equals 0, 2 pi, 4 pi, 6 pi, 8 pi. And the way that we can write that is just 2n pi, where n equals 0 or a positive integer. And then you could just solve that for Dmax, right? So how would you do it? You go Dmax equals, let's say 2n pi, and then we'll take over the theta r, and then we've got to divide it by 2 beta, right? So we could break that out and go 2n pi plus theta r each divided by 2 beta. And then we can go, well, beta equals 2 pi over lambda. So that would be 2n pi divided by 2 times 2 pi over lambda plus theta r divided by 2 times pi over lambda. Well, look, we've got a 2 pi upstairs here and a 2 pi downstairs. So those cancel. And lambda is in the denominator of a denominator. So lambda goes upstairs. So we have n times lambda, and we're still left with that 2. For the other one, well, we have 2 times 2. So we have 4 pi, and then lambda goes upstairs. That's a plus. Okay. N lambda divided by 2, theta r lambda divided by 4 pi. So this is how you can calculate Dmax. So how do you do it in reality? Like, if you actually do it, well, you have to know what gamma is. If you know what the full gamma is, gamma has a magnitude and a phase angle. The phase angle is theta r. In our example before, it was 30 degrees, okay? So that would be 30 degrees, but you wouldn't enter it in degrees there. The giveaway is you got 4 pi down here. The theta r would have to be in radians for this, okay? So you get your theta r in radians, 4 pi, Lambda, we know how to calculate lambda. We did our example before. Lambda is UP over F. You normally have F. You can't assume UP is C, but if it's lossless, you have that simple formula for UP. It's just C divided by the square root of epsilon R. So we can get lambda, and then lambda again, and N, which can be an integer. Now we have this rule here. N either starts at 1 or N starts at 0. Okay. How do you know which one? You just look at this. You don't even really need to do this, because let's assume for a second you forgot this, right? And you just, in your head, you just always thought, well, N can start at 0. Okay. And so you plugged it into this formula, and you said, well, for the first one is going to be at N equals 0, which kills the second term, right? Because it'd be 0 times lambda over 2. So you're just left with this. But let's say your theta R was negative. Now you've got a negative D max. What is a negative D? Think of our diagram. Exactly. It would be a position past the load. That doesn't even make sense, right? It makes no sense. We've got a source, we've got a load, we got a transmission line in between them. Beyond the load, that doesn't mean anything. So you could say, if I got a negative value for D max, that can't be. I would need to have N equal to 1, so that I'm adding something that's going to make D max positive, which is all that this is really saying. It's saying we can't have a negative D max, so that if the theta R is negative, we need to start N at 1, not 0. What about the minimum? Well, same thing, but our cos term there just equals -1, just like we've been talking about, right? And then you'd ask yourself the question, which we already asked. We said, when does that equal -1? So really what you're asking is, like, if you had the cos of x, when, like, what value of x makes cos of x equal to -1, okay? And we said it's pi, but not just pi, it could repeat itself. So here, like, N could be 0, right? So it'd be 2 times 0, that'd be 0, plus 1 times pi, so it'd just be pi. So it's really saying our first minimum corresponds to the case where the thing in the underlined in red there equals pi. Our second one would just be 2 times 1, so it'd be 2 plus 1, 3 pi. So it'd be pi, 3 pi, 5 pi, 7 pi, 9 pi. And you could solve this in the same way as I just did. It's easiest if you let N equal 0. So then the right-hand side is just pi. You can bring over the theta R. You can divide by the 2 beta. You can substitute in the beta equals 2 pi over lambda. Simplify it down a little bit, and you'll get an expression that looks just like the last one, but instead of plus, what did we have? Plus pi over 2. Instead of plus N lambda over 2, we have an N lambda over 4. So they differ by 1/4 of a wavelength. So the easiest way to do this is to just calculate the D max using the way that we just talked about. Then you either have to add lambda over 4 or subtract lambda over 4. How do you know which one? Depends on what you calculated for D max. So it's, once again, this rule comes down to, I can't have a negative value because it doesn't make any sense. So we're going to do an example of this at the beginning of next class, where we'll actually put numbers to this and we'll calculate a D max and a D min. So hopefully that helps. So we already saw standing wave ratio, VSWR, VISWR, SWR, all that stuff. If gamma equals 0, that means we're perfectly matched. So the magnitude of gamma would equal 0. So we'd have 1 plus 0 over 1 minus 0. We'd have an S of 1. That's the best we can do. Okay. S can't go less than 1 because it doesn't make sense. because then your maximum is less than your minimum. It just doesn't make sense, right? So S, if you think about in the other extreme, what if it was an open circuit? Gamma would be 1. If it was a short circuit, gamma would be -1. In both cases, the magnitude of gamma is 1. So look at that denominator, 1 minus 1. It's blowing up. So it can go up to infinity. So all your standing wave ratios are between 1 and infinity. And it's really easy to calculate if you already have the gamma. Okay, so go through the examples 2.5 and 2.6. I would say this is amongst the most difficult thing to visualize or really wrap your head around, because there's a lot of things going on here, right? You've got this time varying signal that's also moving down the transmission line. And then we've got different locations on a transmission line. We've got an incident wave and a reflected wave adding together, creating this constructive and destructive interference. And then we're plotting the envelope or the magnitude of it. So it's really easy to like lose track of what's going on here. So definitely recommend reading this stuff in the book and looking at example 2.5 and 2.6. And then when we come back on Monday, we will start off by doing this example. We'll work through this example. Any final questions? All right. I think that's good then.